Hello everyone, and welcome to our channel, MooTechie. It's wonderful to have you with us today as we dive into a fascinating and important topic that connects our environment, our food, and our health. Let's get started. Now, let's begin with a first slide, titled Occurrence of Radionuclides in Milk and Milk Products. This presentation will cover sources, pathways, safety limits, and health effects. The content is brought to you by MooTechie. Moving forward, we'll explore the introduction, which asks why milk monitoring matters. Radionuclides are defined as unstable atoms that emit radiation during their decay process, releasing energy and particles. Milk is a rapid pathway for these substances after a release. For example, iodine-131 transfers very quickly from animal feed to cow's milk and then to the thyroid. It's especially important to note that children and infants are more sensitive to these effects. Early monitoring helps reduce potential health impacts through timely interventions. Furthermore, routine monitoring programs are essential for verifying low background radiation levels and for quickly detecting any contamination events. The slide is also for MooTechie. As we continue, let's understand the natural sources of radionuclides in milk. Potassium-40, which is part of ubiquitous potassium, is the main natural contributor to radioactivity in milk, typically ranging from 50 to 380 becquerels per kilogram. Then there are the uranium and thorium decay series, including radium-226, lead-210, and polonium-210, which transfer from soil to plants and then into cow's milk. Cosmogenic radionuclides like carbon-14 and trace amounts of tritium, or hydrogen-3, come from natural atmospheric processes. The levels of these can vary based on local geology, soil composition, and the types of feed used, but they typically contribute only a low radiation dose. This information is again from MooTechie. Next, we explore environmental and human-made or anthropogenic sources. These include nuclear accidents or fallout, which release iodine-131, cesium-134 and 137, and strontium-90 into the environment. Historical weapons testing has resulted in global fallout, spreading long-lived radionuclides worldwide. Other sources are industrial and medical releases, and as well as NORM, naturally occurring radioactive material, found in fertilizers from phosphate processing. Factors like resuspension of dust, irrigation practices, and the import of animal feed can all affect how contamination is distributed. Coming up, we'll discuss the specific types of radionuclides found in milk. We have natural ones like K40, Ra26, and Pb210 or PO210. Then there are artificial ones, such as I-131, which is a short-term concern, and cesium-134 and 137, and strontium-90, which are long-lived. Occasionally, others like ruthenium-103 and 106, or plutonium and americium, can be found near specific incident sites. It's interesting to note that the distribution differs in various milk products. For instance, strontium tends to concentrate in curd and cheese. Let's look a bit closer at the natural radionuclides. First, K40 is present in all potassium and is common in many foods. Second, Ra226 comes from the uranium decay series. And third, Pb210 and PO210 come from radon decay products. Now, for the artificial radionuclides. Number one is iodine-131, which has a short half-life of just 8 days and seeks out the thyroid gland. Number two is cesium-134 and 137, which are long-lived and distribute throughout the whole body. And number three is strontium-90, which is also long-lived and is a bone seeker. Let us now look at the pathways these radionuclides take to get into milk. The slide shows a flowchart titled Radionuclide Contamination Pathways into Milk. It illustrates that radionuclides can be deposited from the air onto pasture. Cows then ingest or inhale these contaminants from the pasture. The radionuclides are absorbed in the cow's gastrointestinal tract and then transferred into the milk. Additional pathways include uptake from soil through plant roots, direct ingestion of contaminated water, and the consumption of herbage with soil particles stuck to it. Moving forward, let's explore the mechanisms of transfer and bioaccumulation. The fractional absorption in the gastrointestinal tract, known as Fa, varies depending on the specific element. Scientists use the transfer coefficient, Fm, and the concentration ratio, or Cr, to help estimate the movement into milk. The biological half-life of these substances in milk is about 2 days, meaning there's a rapid decline in concentration once the cow is switched to clean feed. Elements often behave like biological analogs. For example, iodine acts like it does for the thyroid and milk, cesium behaves like calcium for bones, and cesium distributes like it would in muscle. Factors like soil type, season, the animal's diet, and whether their house indoors can all modify this transfer. The slide also includes a simple diagram showing the process from contaminated feed being ingested by the animal to distribution in the blood and finally excretion into milk. There's also a table mentioned which lists parameters like the transfer coefficient in days per kilogram, the biological half-life in days, and the concentration ratio, providing reference values for understanding how radionuclides move into milk. Moving on, we come to the health importance of these radionuclides. Let's take them one by one. Iodine-131 concentrates in the thyroid gland, poses a higher risk for infants and children, and carries a potential risk of thyroid cancer. Its short half-life is 8 days. Cesium-137 distributes throughout the entire body, has a long biological half-life, leads to whole body exposure, and has a 30-year physical half-life. In contrast, potassium-40 is naturally occurring, is an essential element that the body maintains in homeostasis, and presents a low health concern. The important context here is that adhering to established safety limits keeps the public risk very low. Next, we'll discuss safety and regulatory limits. Major regulatory agencies around the world set maximum limits for radionuclides in food to protect consumers, especially following nuclear incidents. Here is a summary of some key limits. For the radionuclide group containing iodine-131, the FDA's derived intervention level is 170 becquerels per kilogram. Codex and WHO recommend 100, and the European Union sets it at 500 for adult foods and 150 for infants. For cesium-134 and 137, the values are FDA 1200, Codex and WHO 1000, and the EU 1250 for adults and 400 for infant foods. For strontium-90, the values are FDA 160, Codex and WHO 100, and the European Union 750 for adults and 75 for infants. It's crucial to note that foods for infants and children often have stricter safety limits because they're more sensitive. These limits apply to becquerels per kilogram of fresh weight, and for powdered products, you need to adjust for the reconstitution factor. For items like spices, which are consumed in very small quantities, higher limits may sometimes apply, considering dilution factors. Now, let's look at how monitoring and detection are carried out. The primary method is using HPGE gamma spectrometry, which is a highly sensitive technique that requires calibrated equipment and has a known minimum detectable activity. For sampling, milk is collected directly from farms or from bulk storage tanks. After an incident, targeted sampling is done first for iodine-131 and then later for cesium and strontium. Screening can also involve gross alpha and beta measurements, with confirmatory tests to identify specific nuclides. All results are reported in becquerels per kilogram, and quality assurance and quality control, including interlaboratory checks, are vital. The process involves several steps. First, in sample collection, fresh milk from the farm or a bulk tank is collected in sterile containers. Second, the sample is prepared. Third, the liquid sample is specifically prepared for spectrometry analysis. And fourth, it is analyzed using the HPGE detection system. The final stage is spectrum analysis, where specific radionuclides are identified and their quantities are measured. Following this, we'll examine the impact on the dairy industry. In an emergency, controls like placing products on hold, segregating them, and executing recall protocols are activated to prevent contaminated products from reaching people. Actions with the animals themselves include switching to clean feeding strategies, housing livestock indoors, and using alternative water sources to reduce radionuclide uptake. There are also processing technologies that can help mitigate the issue, such as ion exchange techniques to remove iodine-131 and strontium-90, or simply storing products to allow short-lived isotopes to decay. All of this has economic impacts, including the cost of testing and certification, challenges to market confidence, and the need to comply with different safety limits for exports. This slide is also from MooTechie. Finally, let's wrap up with a summary and the key takeaways. Milk is a sensitive indicator and a rapid pathway for radionuclides, moving these radioactive materials quickly from the environment to humans. The key nuclides to remember are natural K40, which is a low concern, and the artificial ones, iodine-131 for short-term risk, cesium-137 for long-term presence, and strontium-90 as a bone seeker. Routine monitoring programs and strict adherence to safety limits are fundamental to protecting public health by preventing significant radiation exposure. We must remember that children and infants are the most sensitive to health effects, so their milk products require special attention and stricter limits. In conclusion, clear communication, being prepared, and relying on science-based regulations are what successfully protect both public health and the dairy industry. Thank you. See you in the next class.